You're listening to the Effective Statistician podcast, episode number 50, Introduction to Cluster Analysis. I can't believe we have reached number 50 with this podcast, and we have already a number of other episodes recorded for you. So today we talk about a very, very technical topic, as lots of you have asked me to dive into a couple of more technical talks. So stay tuned for this one. Welcome to the Effective Statistician with Alexander Schacht and Benjamin Pieske, a weekly podcast for statisticians in the health sector designed to improve your leadership skills, widen your business acumen, and enhance your efficiency. If you are not yet following me on LinkedIn, just please connect there. It's a great network and I'm providing regular new content there. I'm sharing ideas, I'm sharing additional content, I'm resharing things that I see there. So lots of great things that you'll get pretty much on a daily basis. In this episode, we talk all about cluster analysis. We go through the different questions that you can answer with cluster analysis. We go into the different ways you can do cluster analysis, especially some metrics that are relevant there. And we also give you a little bit of a heads up in terms of how you can implement that, both with SAS and with R. As this episode is actually based on a webinar that happened in late 2018. And if you're a PSI member, you can go to the video on demand content library and search for the webinar there and see also two other courses about machine learning there. So very, very interesting topic. This podcast is created in association with PSI, a global member organization dedicated to leading and promoting best practice and industry initiatives. Join PSI today to further develop your statistical capabilities with access to the special interest groups, the video on demand content libraries that I just mentioned, free registration to all PSI webinars, like the one where I talked about, and much more. Visit the PSI website at psiweb.org to learn more about PSI activities and become a PSI member today.
Welcome to another episode of The Effective Statistician. Today we are talking, I mean Alexander. Hello, Alexander.
Hi, Benjamin.
And myself, we're talking about cluster analysis. And actually, we're referring a little bit back to November last year when Alexander held a PSI webinar about cluster analysis with the topic of not all patients are created equal, but there are subgroups that are more homogeneous. And so we will put these slides or as a reference in our webpage as well. So it's probably a bit easier for you to follow our conversation today when you have a look at them in parallel or afterwards. But the question today is about cluster analysis. And maybe Alexander, what is the question behind cluster analysis? So what is driving the analysis itself and the people overall just working with cluster analysis?
So in terms of cluster analysis, we have chosen this topic to have really a technical topic because lots of listeners were asking for more content on technical topics. And cluster analysis is a technique that very often people don't usually learn at university or in their career, and it's something that is not very often used, let's say, in the standard setting of clinical trials, because it's not about comparing treatment groups or comparing known groups. It's more about finding patterns, unknown patterns in data. So it's helpful for answers questions such as do you have different segments of patients in your baseline characteristics? Yeah, or do you have certain patterns of time over time in terms of evolution of how the patients go over time and develop over time in terms of the symptoms and things like this. You can also look into things like what are the usual concurrences of adverse events, for example, or lots of other things. So it's very often about, are there, for example, patients that are very similar to each other and that form clusters within the overall patient population.
Okay, so the question is not very, as you said, not very often or frequently asked in usual phase 2-3 trials, let's say. So is this then more about, let's say, the use is more about like what we call maybe data surveillance, so any data checking during the conduction of the trial, or where do you use this then actually? Or is it rather for late phase studies where you dig into the data more and work in to find grouping for patients in NIS trials, for example?
I think it's a set. It's analysis that is also very often used in these big data areas. Mm-hmm. So if you have lots of data and you want to find patterns in there, find segments in there that are more similar to each other, then this is a nice way of exploring data. I think there's lots of different applications. It can be in preclinical, it can be in early phase areas, it can be in late phase areas. And for example, if you want to understand kind of how the different treatments, how the different patients develop over time in terms of their symptoms, are there certain patterns in there? So are there, certain patients that are the very fast responders? Are there the patients that are kind of, late responders? Are there patients that have, respond initially, but then lose the efficacy again? And you can use cluster analysis to identify these different patterns in your data. And then once you have these patterns, you can then try to understand what drives these patterns. What are the kind of known disease characteristics that are associated with that? So it's so to say a statistical learning technique that helps you to identify unknown groups within your in your data. And I think there's, if you think about other areas, you could look into are there patients where the drug doesn't hit the target, or where the pharmacokinetics are kind of off, or other things. So you could look into lots of different data to explore that. But of course, in a real world evidence setting, or in big observational studies, in registries, you could look into very, very large data sets and see, are there kind of distinct clusters within these settings that tell you something about certain patient types, so to say, that are very different. Or one example that I will come to later is actually we looked into patient preferences, and we wanted to understand what are the different types of patients that have distinct types of preferences in terms of different features of medication. So in terms of safety, in terms of tolerability, in terms of efficacy, in terms of convenience, these type of things.
So it's really the question is then really a multidimensional question in terms of
yeah. You always start with, let's say, a vector of lots of data, and let's say it's easiest if this data is all comes from a similar dimension. So if you have kind of, let's say, a couple of visits, and the each symptom measurement at these different visits is one variable, that could be the case. Or if it's a series of binary questions, for example, could also be a very, very easy case. But it also works if you have a combination of all kind of different data. So if you have the usual suspects in terms of baseline characteristics: age, weight, gender, race, disease severity at baseline, certain lab characteristics, whatsoever. So you could, lump these all together in a large factor for each patient, and then put them through cluster analysis to see whether there are certain patient characteristics that basically lump together.
So you already mentioned some of the, let's say, leading questions for the cluster analysis. Is there anything else where you can think of what you could, what is the driver for using cluster analysis?
No, I think that describes probably very good kind of the setting. I think one thing maybe as a complement to that, as a kind of different approach is these approaches where you already know some outcome. So, and then you want to understand what is associated with that. So let's say logistic regression analysis, where you want to understand what is your response is your endpoint, and it's binary, and you want to understand what drives response. And then you have lots of covariates that you put into the logistic regression model to understand what has an impact on the response. Or you have simple regression analysis or other kind of classification analysis. Where you basically look for what are the variables that drive this endpoint. And that is sometimes called supervised learning. So statistical supervised learning, where you look into which variables have an impact on this endpoint that you know. And this endpoint, so to say, supervises the learning algorithm. And cluster analysis is in that regard an unsupervised learning algorithm, because you don't know what kind of patterns you will find. You don't know whether you'll find 3 groups, 4 groups, 5 groups. So that is one way. And cluster analysis is one way in terms of unsupervised learning. Another completely different technique is associated with dimensional reduction. So things in the direction of principal component analysis, these kind of things, where you try to, reduce dimensionality in that regard. That's another kind of example.
Okay, so I mean, talking about, like, if you have a specific question, it's probably easy to understand how you cluster, how you would cluster as an investigator, let's say, to cluster patients, because, following a logic. But how do you do this technically? So what is the technique of clustering that we follow, and maybe different approaches? I mean, I do remember areas where what's probably coming in here at some point is, when we had still back in university times, when we talked about numerical, finding local optimum, meaning that we had, different measures of distances between points, and kind of found the position where it was optimal with regard to one or the other dimension, or whatever measure was taken for this one. But how is it in statistics? So how do we use technically clustering here?
Yeah, so as I said, it goes into the direction that you're speaking about. You have these, you can think of each patient, or each unit, subject, whatever, has a vector of variables. And now you need to find vectors that are close to each other. And the mathematical problem now is to define what close means. What does similar mean? And of course, you can come up with all kind of different metrics to group patients together. And that's also where a little bit the art comes into place here, because this is not kind of a black and white exercise. This is more kind of an exploratory analysis to find the right metrics that gives you interpretable results, meaningful results that you can then further work with. So that's...
Yeah, I imagine it's also difficult for, especially if you have a vector of different types of variables. So meaning that for one would be one metrics, the ideal and interpretable, especially if we talk about interpretation, way of defining the distance or the closest they are together, and for others it just doesn't work. So do you have different matrices for different variables then within one cluster analysis, or is this not the case?
No, you would have defined one metric for all the different variables in your vector. However, of course, you can play with that a little bit in terms of how you standardize things. So you can start, for example, by standardizing all your variables so that all have a standard deviation of 1, and start with that. And then, maybe using certain variables are more important than others, and you multiply them, and then they get more weight later on. So that's, of course, some initial steps that you could do. The other initial step, of course, is to maybe put in only those that are where you think are really relevant, and not put into too many noise, because, well, with these techniques, the more garbage you put in, the more garbage you get out, and it's the more uninteresting data you have in there. Of course, the less easier it is to find something. Yeah.
Okay, before we go to the ways of how to define these metrics or distances between patients in this case, so how is it then done how's the clustering actually done? So just imagine you find two narrow patients. So what do you do about these two patients, and how do you go on? Because I suppose you would like to have a number of, like a grouping or bigger clusters than only two patients, finding a pair of patients.
Yeah. So today we just talk about hierarchical clustering, and that works very, very easy. Think of as a first step, each patient is one cluster. Yeah. In the next step, you find the two closest clusters and combine them. And then after this third step, you have one cluster less than before, because you have combined two clusters. Then you start again. You find the next two clusters that are closest together and combine them again. So that now you have one step further, and you have two clusters less. And so you repeat these steps until you only have one cluster left. And that way, if you view that on a graphical thing, you can see how these different clusters are related to each other, and display that very, very nicely with a dendrogram. Yeah. So where on the left-hand side you have one line that is, goes from parallel lines that start from the top to the bottom, and where each line represents one cluster, and in this case, just one patient. And then the further you go to the right-hand side, the more you see how the clusters get together. So in the webinar, I actually present an example with a couple of cities of North America, and you combine them in terms of the smallest distance to each other. And so at the beginning, you have their cities like Seattle, San Francisco, LA, Houston, Denver, and so on, Washington, New York. And then you look into all these different cities. What is their first, smallest cluster? You combine Washington and New York. Yeah. And then, in a later cluster, you combine Chicago and Atlanta. And then in a later cluster, you combine the cluster that has Washington and New York in it together with a cluster of Chicago and Atlanta. Yeah. So that way you move on and get bigger and bigger clusters with each step. And now, of course, kind of the question is, when do you stop? Yeah. So what is a good balance between, having reasonable number of clusters? Yeah. Because, you can see it also from this is again coming back to this classical variance bias trade-off. So if you want to be very, very precise, you need to have lots of clusters. But then within each cluster, there's only very few patients. So you're very unbiased, but also very unprecise, because, with only a few patients in a cluster, you can't measure anything very precisely. Yep. If you go on the other end and you have very few clusters, then, of course, within each cluster, there's lots of patients. So anything that you measure within these clusters gets very, very precise. But, of course, you're potentially combining things together that don't belong to each other. So you get more bias. So there is this kind of, and you can look into a little bit of different ways to assess what's a good cluster, but we'll go into that a little bit deep later in the podcast today.
Okay, as we talked about these quite geographically and nicely imaginable ways of combining the cities of North America. So, but how does it then technically work? So if you have a cluster and combine Washington, D.C. and New York together, so how do you now start to measure the distance? Is this the mean between, or the geographically mean between the two cities, or how is this then defined in when you say combining two patients or two clusters together?
And now we are getting actually to the core of the problem, because defining this distance is you need to have a distance that also takes into account that you have more than just one observation in that. So it needs to be meaningful also for clusters that have bigger number of patients in it, or in this case cities. And in this episode today, we just talk about, from a notation point of view, I'll use the SAS notation. The R notation is a little bit different, but not so far off in terms of how the different programs use that. But we want to cover 6 different distances today that each has its pros and cons. Yeah. So, and these distances, just as an overview, are called single, complete, average, centroid, case nearest neighbor, and ward.
Okay, so let's start with the single one.
Okay, so the single one. You can, just if you want to go back to the slides, and you will have also notations there. And also the mathematical, very exact kind of notation of how this is designed. But as a listener now, you can just imagine single means you look into the minimum distance between an observation in one cluster and an observation in the other cluster. So let's say you have combined, maybe Philadelphia and New York in one cluster. Now you want to look into another cluster that contains, let's say, Boston. Yeah. And Boston and New York are the closest to each other. And, the distance between Boston and New York is the distance you're looking into.
A single distance. Okay.
Yeah. And what's nice about this is that it puts no constraints on the shape of the clusters. And therefore, it's good in finding very elongated or irregular clusters. But that is also kind of the con side, because you may get into kind of weird chains, basically, where just one very close to each other is combined. And there is the option that you could also combine that with trimmings, that that you add some features that there's some kind of that you cut the chains at a certain point. Yeah, so that is an additional option there. So, but that's I think a very, very intuitive way. Yeah. So you look into two sets of observations. You look into all the different possible distances between the single elements in these two sets, and then you look into the minimum of that. Yeah.
Yeah, this is nicely, again, going back to the cities of Northern America. It's good easily to imagine how this would work here.
Yeah. And the next distance is also very easy to understand from that point of view. It's in some sense kind of the opposite. It's called complete. And there, instead of looking into the minimum, you look into the maximum. Yeah. So you have two sets of, let's say, cities, and then you look into what is the biggest difference between any pair of two elements from the two sets. Yeah. So
that obviously helps you to get the if you imagine this as a cloud or as a group, to really find the ones that are overall the nearest to each other.
Yeah. And this is a technique that tends to produce clusters that have equal diameters. Yeah, so that is a property of that technique, and it's also very sensitive to outliers. Yeah, as you can imagine, if you look into maximums. So,
and the third one is what I would think is actually the most intuitive.
Yeah, so that is a very easy one. So instead of looking into the minimum of all the pairs in terms of their distances, or the maximum, you look into the average of all the pairs of the things. So that tends to look into it's a little bit like minimizing squares, least square means kind of thing. And so it tends to join clusters with small variances together, and is therefore usually producing clusters with similar variance. So it's it's a nice approach because I think it's pretty easy to understand. It's not sensitive to outliers. Yeah, it doesn't have this chaining effect. So yeah.
Yeah, but again, I think it's I agree. I think if you have many clusters to join, then there's I think the danger or the need to to check with the interpretation and double check is as you said, the bias then towards the similar variances that they are really not. But I think if it's only a few clusters left, then or overall, then I think this is quite straightforward.
Yeah, and you can imagine if we think about these kind of things, and you think about big data, these are very computational intensive algorithms.
Yep.
Yeah,
indeed.
So just from thinking about, okay, you need to compute all differences for all pairs, for all clusters. Okay.
Yeah, but I think the more intense or the more computational intense ones, they're still coming, aren't they?
Let's see. I think they are all pretty intense. I think the next one is actually not that intense. It's pretty easy because that's a centroid one, and there you just need to know the midpoint, so to say, of the cluster. So if you think about kind of North America, yeah, and the cities there, you take the Euclidean distance between the centers of these clusters. Yeah. So basically, for each cluster, you just need to compute what is the midpoint, and then you look into join those clusters that have the least difference between the midpoints. So that's not very resource intensive.
And I think it's good as well for to imagine how it works, so to explain how the technique is working.
Yeah, and that's of course pretty robust to outliers. Yeah. Now we get into a little bit of a more interesting one. That is the case nearest neighbor approach. And so there you give, let's say it's more kind of, how should I say it? How can I get it? This is okay. In terms of that distance, it basically gives you some kind of density of the observations in a sphere around a certain observation. So you look into, you define basically what the distance is for one observation to the case nearest neighbor. Yeah, so to the first nearest neighbor, second nearest neighbor, third, fifth nearest neighbor. Mm-hmm. Yeah, and then you look how big is the density of the observation in that sphere. Yeah, and you basically define the distance then as the you take the inverse of that density and you add up these inverse of the densities to come up with the distance. And so that basically puts, looks into a sphere around the observations and looks how dense the observations are in that area. And therefore, it produces also high density clusters. So it looks kind of, in that regard. And you could also kind of think about it, of course, you could look into all kind of other kind of kernels around that. So other distributions that you've basically fit around the observations to, describes the to basically smooth the density. Yeah.
And how do you then define, or like how do you choose then the clusters, or how do you define where the two clusters which two clusters you combine then further on?
Well, with that kind of way, you get again kind of a distance, and you combine again then those that has the smallest distance.
Okay.
Yeah. Okay. That's a little bit more a complex one. And that is the most complex one.
Nice looking formula.
Yeah, nice looking formula. But I don't want to kind of describe that now to the listeners. But if you're interested, really go to the slides and then check these things out. And there's also a very, very nice SAS documentation about that and an R documentation. And actually, that is also referenced in the slides later on, or you just go to our homepage where we will have the links to the software packages. So there's SAS Pro Cluster that has that, and the R package has also the very innovative name of Cluster. So, okay, let's get to the.
But there's
there's one left, and that's the ward method. That I actually applied also in some examples, and I found it very kind of intuitive as well, because it looks into the ANOVA sum of squares between two clusters, added up over all the variables, and it basically minimizes the within cluster sum of squares at each step. So it really looks into kind of that clusters forms in that way that you really the sum of squares gets increased, minimizes the increase in terms of the sum of squares. And so that also joins small clusters and usually gives roughly equal sized clusters. It's sensitive to outliers, but in the approaches where I worked with, I didn't have that problem.
Yeah, that's quite normal for the ANOVA sum of squares.
One of the things is really, as you've seen, you have lots of choices, and this is, of course, on one side good, but on the other side bad, because you have the curse of choice, so to say.
Yeah, I think there's the good thing is that you can really give it a try. I mean, as we said, it's often for digging into the data, understanding the data. So it is really give yourself time to find out which is the best and which to apply. And it may, and also maybe for one set of data, it may work with one. For another set with data with the same variable, it may not work for one because of the observations that you really have. So there's no rule really how to say, if you have this, then do this. It's really driven by the data.
I think what I would usually do is I would apply various approaches, and I would check for robustness. So looking into outliers, running it with and with outliers. For some of the algorithms, you can use trimming in addition. You also need to look into the number of clusters, and there's, of course, you can look into kind of this bias variance trade-off measures. But what I also really look into is the interpretability. So does these clusters tell you a story? Can you, make sense of them? And so what I usually do is I program in such a way that I have all the characteristics for the clusters produced at the same time, so that I can see, okay, does these clusters tell me something? Is there some kind of good medical interpretation in these clusters? Like I earlier mentioned, is there, a cluster with a rapid onset? Is there a cluster with, very strong preference for efficacy in patient preference survey data? Or is there, some cluster that has a meaningful interpretation? And then I look into kind of, if I split these clusters up, do I then have, two clusters that have basically the same interpretation, more or less? Then, well, I don't need to split them anymore. Usually you don't want to have unreasonably small or large clusters. If you have one cluster that kind of contains 99% of your data, unless you're looking maybe for fraud, that's a bad thing.
No, but I think good help for these choices and the interpretation of the data is really to have it visualized. I think this is a big help, really, to have it visualized, use colors. I think there are good examples in here in the slides as well. So where you really see with different colors where these individual data points are located, and then see, if it tells you a story, if it makes sense to you.
And with these colors, you can see also combine the colors in the patient characteristics, so that you see, okay, the blue color, the blue cluster has lots of female patients. The red cluster has lots of severe patients. And so that you can very, very then easily see. And you can also see, if you look back into your dendrogram with, where did you split? How that then relates back to if you split further, does it make sense or not? So that is really more an art than the science. And of course, one other thing to have in mind is the more data you have, the more patients you have. So not the more data, but the more patients, the more units, subjects you have. Of course, you could allow for more clusters. Yeah, because then you still have possibly within the clusters still enough data. But of course, in the end, you probably don't want to come up with 50 clusters. Who wants to interpret that? Yeah. So.
Yeah, exactly. I think it's usually less. I would say like a handful, maybe two.
Let's talk about a couple of very practical topics. First topic is missing data. So of course, especially if you have more kind of observational data, lots of variables will be kind of missing. One thing for the categorical variables is what is a very, very nice approach to treat missing as its own category, because sometimes that's informative. And of course, for the continuous analysis, you could impute that somehow. Yeah. So, and inform kind of the correlation metrics there. Of course, you could even combine it with kind of multiple imputation approaches, but I think then it gets really, really fuzzy, because you would have for each imputation, you would have its own run on clusters. Of course,
your own check and your own thoughts. And your own interpretation.
It gets pretty messy, pretty fast. Looking for outliers is certainly something to do to run the analysis without outliers. And of course, it's important to look for correlated data, because these could, have a huge impact on the cluster. So just imagine you have, let's say, have 9 highly correlated variables and one that is not correlated with these, and the clusters would mostly be driven by these 9 highly correlated values. And just need to be aware about that.
I think that really goes to it's one of the initial questions really, to what data to use. So.
Okay, and with that, I think I would just refer you to the slides, because there you can find some nice pictures in terms of 2 example cases where I looked into this. I already mentioned, these in the beginning. One was a patient preference survey where we had 7 binary questions and looked into that. We had 500 patients and came up with 4 different clusters. And another approach we had a couple of observations over 3 years from an observational study, and we looked into the quality of life, how that developed over time, and we found 4 distinct clusters that behave very, very differently. 3 that actually were rather stable over time, or just generally getting better a little bit, and 1 cluster that has a very, very fast onset of action and then stayed stable over time. And it was very, very interesting then to look into what determined this cluster.
Okay, and also in the slides there are some more references. So to dig into this to more detail and find some more ideas where to read and what to read. And also there's some more reference, what we already mentioned, to the software to use, so the proc cluster and SaaS, or the cluster package. So this is a little bit more where you can find some support there.
Okay, awesome.
And with that, thanks, Alexander, for rerunning the presentation on the cluster for the listeners.
Actually, it's not a rerun. It's a complete new content with all the question and answers. And I had much more time to go into this content here than I had at the webinar. So,
okay, perfect. All right, then.
Talk to you next week.
See you next time.
This show was created in association with PSI, and next week we chat with Kate Taylor, who is the conference chair of this year's PSI conference. So check that out, and thanks for listening. And especially for the episode today, visit theeffectivestatistician.com to find the show notes and learn more about our podcast to boost your career as a statistician in the health sector. Today you'll find there also, for example, a link to the slides that I used for the webinar.